Hello, everyone, and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Materials Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or tutoring, then check out the links in the description below. So now let's just get started on our set of questions for today's session. Okay, so question 1 asks, how can I calculate the bond order of benzene? Okay, so first I'll just draw out the benzene molecule. It is a 6-membered carbon ring, and it is also aromatic. So we can tell that a molecule is aromatic, and most of the time there's like a double bond in between every other atom, like this. And now each carbon contains a hydrogen as well. So you can see that this molecule contains both single and double bonds. Okay, so now I'll just write down the formula to find bonding order. This is equal to the bonding electrons minus the anti-bonding electrons all over 2. Okay, so I'll answer this question in 2 parts. So for the first part, I'll just write down that each sigma bond contains 2 electrons. So therefore, the bonding electrons is equal to 2, and the anti-bonding electrons, let's put ABE, is equal to 0. So I can calculate the bond order for the sigma bonds. So it's going to be 2 minus 0 divided by 2, which is equal to 1. Okay, so for the second part of this question, I'll also write that benzene contains 3 pi orbitals. So this can be seen with all the double bonds that are in benzene. So since there are 3 pi orbitals, there are 6 pi electrons. Okay, so let me write down the bonding order of the total pi bonds in the molecule. So the bond order of 3 is for the total pi bonds. But for each pi bond, I'm going to divide the 3 by 6, since there are 6 pi electrons. So this bond order is 0.5. And now, third part, I'll just put it both together. So the total bond order for each carbon-carbon bond is 1 plus 0.5, which is 1.5. Okay, so now let's see what the junior tutor said. Total bond order of benzene is the sum of the bond order of the carbon-carbon sigma bonds and carbon-carbon pi bonds. The formula for the bond order is bonding electrons minus anti-bonding electrons divided by 2. For the carbon-carbon sigma bonds, for every carbon-carbon bond, there are 2 bonding electrons and no anti-bonding electrons. Thus, the bond order is 2 minus 0 divided by 2, which is equal to 1. Carbon-carbon pi bonds. There are 6 delocalized pi bonds. For the carbon-carbon bonds, the 6 pi bonds belong to the bonding orbitals. Thus, it has 6 bonding electrons. So 6 minus 0 divided by 2 is equal to 3. Since there are 6 carbon-carbon bonds, the bond order for pi bonds will be divided into 6. So for every carbon-carbon bond, the bond order is equal to 0.5. So the sum of the bond order of sigma and pi bonds for every carbon-carbon bond is 1.5. Yep. So the solution is correct. Okay, so on to question 2. How can I determine the Van 't Hoff factor of a substance from its formula? Okay, so first I'll just write down the definition of the Van 't Hoff factor. Which can be denoted as I. This is the number of particles formed in a solution from one formula unit of a solute. So depending on whether or not you have a non-electrolyte or a strong electrolyte, this will affect the Van 't Hoff factor. So for example, for non-electrolytes, so non-electrolytes are when ions, when the solution doesn't separate into its ions, or the solute. I'll just write that down. So non-electrolytes, they don't separate into ions in solution. So these are like non-conductive metals, and their Van Hoft factor is typically equal to 1. And when you have a strong electrolyte, like sodium chloride, its Van Hoft factor is greater than 1. Okay, so let's see what the junior tutor said. The Van Hoff factor I is the number of particles each solute formula unit breaks apart into when it dissolves. It can be determined depending on the type of solute, non-electrolyte, or electrolyte. For non-electrolytes, the solute will dissociate into ions, therefore I is equal to 1. For example, sucrose. For strong electrolytes, I is greater than 1. For example, sodium chloride will dissociate according to the reaction NaCl makes Na plus Cl minus. Thus, I is equal to 2. For magnesium chloride, it will dissociate according to the reaction MgCl2 makes Mg2 plus 2 Cl minus. Thus, I is equal to 3. So they're pretty much counting how many ions forms after it is dissociated into the solution. For weak electrolytes, I can be calculated using the ICE table. So they have an example using the weak acids, HA, that dissociates into H3O plus and A minus. And the ICE table stands for initial, which is the initial concentration. So notice that the reactant starts off with a concentration of 1, and two products start with 0 because they aren't formed yet in the initial reaction. The change is how they change in concentration, and then at equilibrium, 1 minus X and for the reactant, and the products are just X. So at equilibrium, the total number of moles is equal to 1 minus 1 X in brackets plus X, which is equal to 1 plus X. Yep, so those are all the ways of finding the Van Hoft factor. So the solution is correct. Okay, so on to question number 3. What is STP in chemistry? Okay, so pretty straightforward question. STP stands for standard temperature. And pressure. So at STP, that means your temperature is equal to 273 Kelvin or 0 degrees Celsius. And for your pressure, this is equal to 1 atm or 101.325 pascals, kilopascals. Okay, so the junior tutor said, in chemistry, STP means that the system is in standard temperature and pressure. At this condition, the value of temperature is 273 Kelvin, which is also equal to 0 degrees Celsius, while the pressure is equal to 1 atm. Yep, so this solution is correct. Okay, so question 4 asks, which pair of compounds will form a buffer in an aqueous solution? Okay, so first I'll just write down the definition of what a buffer is. It is a mixture of either a weak acid and its conjugate base, or a weak base and its conjugate acid. So the role of the buffer is that its pH changes very little when a small amount of either strong base or acid is added. So if you were to put like half of a milliliter of a strong base, such as sodium hydroxide, typically in like water or in a normal solution, the pH would become more basic and decrease very fast. But if you had a buffer solution and added the same amount of sodium hydroxide, then it wouldn't change so drastically. Okay, so now let's look at all the options in the question and see whether or not they will form a buffer in aqueous solution. Okay, so we have HCN and sodium cyanide. So HCN is a weak acid, and the sodium cyanide contains the cyanide ion, which is the conjugate base. So therefore, this will form a buffer solution. B, we have HCN again, which is a weak acid, and HCl. So this is a strong acid. So mixing the two acids together will not make a buffer solution. C, we have a strong acid, which is HCl, and we also have a strong base, NaOH. So since they are both strong, they'll just neutralize each other and won't form a buffer, so therefore no. And then lastly, we have the sodium cyanide ion again. Reacting with a strong base. So these are pretty much two bases. So this will also be no. So the answer is just A. Okay, so the junior tutor said that a buffer solution must contain a weak acid and a source that contains its conjugate base, or a weak base and a source of that conjugate, its conjugate acid. think there's just a little typo, but it's kind of minor. And then let's check each pair if they can form a buffer in an aqueous solution. So for the first option, HCN is a weak acid and its conjugate base is the Cn- ion. Okay, so they also showed the reaction that takes place, and its pair is a salt that contains the cyanide ion. Thus, this pair can form a buffer solution. Okay, so for the part B, weak acid and HCl is a strong acid. This will not form a buffer solution. HCl is a strong acid, while NaOH is a strong base. The reaction between the two is a neutralization process, so they will not make a buffer solution. And then lastly, sodium cyanide is a salt that contains the conjugate base of HCN. Sodium hydroxide is a strong base. Base plus base will not form a buffer solution. Yep, so this solution is correct. Okay, so on to question number 5. This molecule is used to make methyl esters from carboxylic acids. Using curved arrows, how should the arrows point in order to convert the structure from one to its right? And B, which contributing structure makes the largest contribution to the hybrid? So what they mean for part B is like which structure is kind of like the more favored out of the three. Okay, so let me just write down the 3 molecules. So first we have a positively charged nitrogen, and then a negatively charged carbon. So these typically aren't that stable, and the negative charge comes down to form a double bond, and it neutralizes the nitrogen for a bit until this triple bond comes down onto the second nitrogen. So this gives us our second structure, which just has 2 double bonds, 1 for each of the nitrogens. And now the nitrogen on the right is negatively charged. Okay, so now one of the double bonds from here comes in and gives the second nitrogen another negative charge, so that it becomes 2-. And then its resulting structure is a single bonded nitrogen with a 2- charge. Okay, so these are the mechanisms. And then for the second part of the question, let's label these different structures A, B, and C. Okay, so typically, the more electronegative atom usually contains the positive charge. So in the case of structure C, the nitrogen is more electronegative than carbon, so it will carry out the 2- charge. So I'm just going to write down that C makes the largest contribution. Since the negative charge is in the more electronegative atom. Okay, so let's see what the junior tutor said. They showed the lone pair on the carbon coming down to form a double bond, the triple bond becoming a double bond to get structure B. And then in structure B, the second double bond comes in and gives the second nitrogen a -2 charge. And then for part B, the third has the highest contribution since it is the most stable among the three. And the charge of the carbon atom and one of the nitrogen atoms is equal to 0. The negative charge in this structure is in the more electronegative atom. Yep. So this solution is correct. Okay, so on to question 6. A generic gas X is placed in a sealed glass jar and decomposes to form gaseous Y and solid Z in the following reaction. So let me write down this as well. 2X as a gas decomposes and forms Y plus Z. How are these equilibrium quantities affected? By the initial amount of X placed in the container. Assume constant temperature. Okay, so I'll just write down all the different quantities that are affected by the initial amount of X. So when the concentration of X changes, then both the mass of Z, which is the product, this changes as well. Obviously, because the more X you have as a reactant, the more Z solid can be produced. So when the concentration of X changes, then the two gases, which is X and Y, their concentrations change as well. So obviously for X, that will change, and the concentration of Y at equilibrium changes. Okay, so since Y is a gas as well, if there was more or less of our initial X, then that means the pressure inside this sealed glass jar will change as well. So I'm going to just say total pressure changes. And the only thing that stays constant is kind of the rate of reaction between the two gases, X and Y. This at equilibrium is constant. Okay, so let's see what the junior tutor said. A decomposition reaction is a reaction where a reactant breaks down into two or more products. In this decomposition reaction, it can be said that the rate of the decomposition does not depend on the amount of substance initially. Yep. So this last point can be described as the rate of decomposition. And the reason why the X is squared is because in the balanced chemical equation, there is a coefficient of 2 in front of the X. So that's why it's important to balance your reaction equations, because this in turn will affect the rate of the reaction. Okay, so to continue, it can be said the rate of decomposition does not depend on the amount of substance initially. In the problem, the compound disappears and new two compounds appear. The rate of the reaction is usually observed by watching the disappearance of a reactant or the appearance of product. In general, it is the change in concentration over the change in time. Okay, so they show how you would find the rate of the reaction is equal to minus 1 over n times the change in concentration of reactant divided by the change in time, which should also be the same rate as the concentration of products, the change in the concentration of products over the change in time. Yep, so this solution is correct. I'll also just add all the other equilibrium quantities. Okay, so I said that this solution is correct. The rate of the reaction at equilibrium is constant. Factors that are affected by the change in the concentration of X are output X, the mass, are the mass of Z formed, the concentration of X and Y at equilibrium, and the total pressure. Okay, so on to question number 7. How do you calculate the vapor pressure of ethanol? Okay, so the vapor pressure can be calculated using the Clausius-Clapeyron equation. Clausius-Clapeyron. Okay, so I'll just quickly write down what that is. So you can use the Clausius-Clapeyron equation when a question asks you to solve for something that changes depending on, like, either if temperature changes or pressure changes, what is the new, like, let's say if the temperature was increased to this and it started at room temperature at this pressure, then what is the new pressure, kind of thing. You can use the Clausius-Clapeyron equation. Okay, so I'll just have like an example question on how we would calculate the vapor pressure of ethanol. So for example, what is the vapor pressure of ethanol at 50 degrees Celsius? Okay, so using the Clausius-Clapeyron equation, R is a constant, so I'll just write it down up here where it came from. And its units, it is 8.314, which is the ideal gas constant. And the units are joules over Kelvin times mole. And another important variable that we need is the enthalpy of vaporization of ethanol in standard conditions. So this is something that is given in a table, like in your textbook, or it might be given in the question. But I'm just going to look it up on Google. So enthalpy vaporization standard values. I'll just put ethanol. Okay, so let me just try to find. Okay, so here is here are the enthalpy of vaporization of different compounds. So ethanol is the same thing as ethyl alcohol. So here it is 38.56 kilojoules per mole. But since our R value is in joules, I'm going to convert from kilojoules to joules for the enthalpy of vaporization value. So that's a J if you can't see it. And this can be converted to joules, 38,560 joules per mole. Okay, so now that we have those two constants, I want to also convert 50 degrees Celsius to joules. So let's see. T1, which is T initial, is equal to 50 degrees. So if we add 273.15, we get T1 is equal to 323.15 Kelvin. And then I also want to find the boiling point of ethanol as well, since that should be given in a question. So it's around 78.4. And we also want to convert this to Kelvin. Which is 351.55 Kelvin. Okay, so P2, I'll just make standard, which is 760 torr. And we are looking for P1, which is the vapor pressure of ethanol at 50 degrees. So this will be question mark. Okay, so we have pretty much all the information we need, and we just need to plug it into the Clausius-Clapeyron equation. So P2 is equal to 760 torr, and we're looking for P1. The enthalpy of vaporization of ethanol we found was 38,560 joules per mole. The R value we are using is the 8.314 joules over Kelvin times mole. And then in brackets, we have 1 over 323.15 minus 1 over 351.55. Okay, so if we solve the right part of our equation, by plugging it all into like a calculator, always make sure to do the reactions that are the equations that are in the brackets first, just because it makes it easier to calculate everything. You should end up getting around 1.159. And then to get rid of the ln on the left side, you take e to the power of both sides. Forget what this term is called. Which is 3.188. And then finally, we just isolate P1 by doing 760 torr divided by 3.188. And we end up with 238.3 torr. So this is the vapor pressure of ethanol at 50 degrees. Okay, so let's see what the junior tutor said. Vapor pressure can also be called the enthalpy of vaporization, denoted by delta H vap. So that's not actually correct. But they also have the Clausius-Clapeyron equation. R is the ideal gas constant, P is the pressure, and T is the temperature. So the units of enthalpy of vaporization is in kilojoules per mole or in joules per mole. And the units for vapor pressure we have can be in torr or ATM. But already we can see that they are not the same thing. But indeed, yes, the Clausius-Clapeyron can be used and then I'll just write down the equation that I have, which shows how to calculate it if you had all these different values. It's always confusing to write multiple brackets, but yep. Okay, so next we'll move on to question number 8, which just asks, what is the relationship between boiling point and vapor pressure? Okay, so to answer this, I think it's just easier to write down the definition of boiling point. So as we all know, this is the temperature where your liquid turns to vapor or gas. But it is also when the vapor pressure of a liquid is equal to the pressure surrounding the liquid. Okay, so that is how the two can be related. So again, the boiling point is the temperature where the liquid turns to gas, and it is also when the vapor pressure of that liquid is equal to the pressure surrounding the liquid. Okay, so we can see what the junior tutor said. Typically, we think of the boiling point as the temperature where a liquid vaporizes. However, another way of looking at the boiling point is that it is the temperature at which the vapor pressure equals the external pressure. Recall that vapor pressure is the pressure exerted by the gas at equilibrium on a liquid or solid in a closed container. That means if I have a closed bottle of water, there is a vapor pressure exerted by the gaseous water molecules on the surface of the liquid water. Going back to the boiling point, when a substance is boiling, its vapor pressure is equal to the external pressure. Under normal circumstances, the external pressure is 1 atm. So the normal boiling point of a substance is the temperature where the vapor pressure is equal to 1 atm. That means that if the vapor pressure increases, the boiling point decreases. The reverse is typically seen in solutions. When we have a non-volatile solute in solution, the solute decreases the vapor pressure of the liquid, which increases the boiling point of the liquid. That is, the boiling point of the solution of the liquid is higher than the boiling point of the same pure liquid. This is called the boiling point elevation. Yep, so for the last part, that makes sense a bit, but it takes a couple readings to try and understand completely. But I'll say the solution is correct. Yeah, I know it sounds a bit confusing at first when we talk about the vapor pressure and then we talk about external pressure. But the more you kind of think about the process, about how vapor is formed, and how if it was in a closed system, then that causes more of the vapor pressure exerted by the gas that is formed. But this solution is correct. And I think we have time for one more question, which just asks, what are organic nutrients? Organic Okay, so if we try to dissect the word or try to dissect organic nutrients, when something is organic, this means that it will contain carbon, so I'll just underline the 2. And for nutrients, these are essential to our health and our bodies need them to function pretty much. So some examples of organic nutrients can be like vitamins, carbohydrates. So we use carbohydrates as kind of like our energy source from like foods and bread, and protein, which is good for like our muscles, and lipids, which are in the fat cells of our body, which is mainly we use them for insulation and other roles of the human body. Okay, so let's see what the junior tutor said. Nutrients in general are substances that can be found in food and are essential to life and health. They allow our bodies to acquire energy for metabolism, build cells and tissues, and maintain our regulatory processes. Nutrients can be classified as either organic or inorganic. The main difference between the two is organic nutrients have carbon, while inorganic substances do not have. Examples of organic nutrients are vitamins and energy-providing compounds, while inorganic nutrients include just like selenium, iron, and magnesium, etc. Yep, so I'll also just write here that you can say that the inorganic nutrients, they can include just like the metals on their own without any carbon. Yep, so I can verify that this solution is correct. Great answer. Okay, so those are all the questions that we have for today's session. And if you enjoyed today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. If you'd like to submit a question of your own, then check out the links in the description. And also, if you liked today's video, you can go ahead and leave it a thumbs up and a comment. And don't forget to share with your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.